Hello students, today we are starting with the chapter on electromagnetic induction. There are different topics discussed in this chapter. Today's discussion we are taking the introduction part, Faraday's laws and Lenz's law. Now in the beginning, Oysted's experiments all of you have studied in the lower classes and which has proved a clear relation between electricity and magnetism. And we will just refresh back that experiments and see the experiment here. There is a battery and a conductor is connected to a switch and a magnet is placed below that, below the conductor. You can see as you switch on the circuit, the magnetic needle gets deflected. So the deflection is from north to west in this case. Now see the second circuit diagram. Here the direction of current is opposite to the direction as in the first diagram. And here when you close the circuit, the direction of deflection of the magnet is in the opposite direction. Which means that there is the deflection of the magnetic needle detects the presence of a magnetic field, which means due to the movement of current in the circuit, a magnetic field is produced, which clearly indicates a relation between electricity and magnetism. So here, which made the scientists to think whether or is it possible to produce electric currents with the help of moving magnets or moving magnetic field. With this question led many scientists to take up experiments relating to that, and finally the conclusion was the discovery of electromagnetic induction, which we are discussing today. Among the scientists who had done experiments relating to the discovery of electromagnetic induction, Faraday was the prominent among them, and the discovery of electromagnetic induction was mainly named after Michael Faraday. And you have studied that the concept of electric field, concept of lines of force, all was introduced by Michael Faraday in electromagnetic induction.
Way I have
See, the magnet is coming in, current is flowing in one direction. When the magnet is moving out, the current is in the opposite direction. So it is very clear that only when the magnet is moving, there is a current produced. And also, you can see that when the magnet is moving in, the direction of current is in one direction, and when the magnet is moving out, the direction of current is opposite to the direction in which the current was moving. And also, suppose you change the polarity of the magnet, when the south pole is coming in, the direction of current is opposite to what it was when north pole was coming in, as well as when south pole is coming out of the coil, then again the direction of current is opposite to that. So you can see that the amount of current that is produced in the circuit is proportional to the movement of the magnet. That is, as far as there is relative motion between the coil and the magnet, a current is produced in the coil. Now, when it is at rest, there is no current produced. These are the observations that are made on the basis of this. Now, instead of moving the magnet, if we move the coil, will there be current produced? Certainly there will be production of current. Now, when you are moving the coil towards the magnet, what happens there? Again, there will be a current generated in the coil. And when the magnet is moving towards the coil with higher speed, you can see there will be a higher current produced in the circuit. And also, then if you move towards the next part, have used a coil connected to a light bulb. That means in order to, instead of a galvanometer, I have connected a bulb here which shows the presence of current in the circuit. And here in this first circuit, there is no source of EMF here. There is no source from which will supply current for glowing the bulb. Now, you take the another coil that is connected to a rheostat, key and a cell. So this is a complete circuit. When you close the key, what happens? A current starts flowing through this coil. Now when this coil and these two coils are facing each other, when these two coils are facing each other, you are keeping these two connections in such a way that the face of this coil is facing the other coil. Now we will see what happens when the key is closed. When the key is closed, you see the light bulb glows with the current flowing through the second cell. Now second coil. So here the first cell, if I call as the primary cell, and the second coil if I call as the secondary coil, this is the primary coil and this is the secondary coil. When I close the circuit, here now it is open. When I close the circuit, what happens? The current flows through the secondary coil and the bulb glows here. It is a sudden process. As soon as you close it, see here it is open. Now when you close it, you can see just a current is passing and it is bulb starts glowing. Now you see when I open the circuit, what happens? When I open the circuit, again there will be a current produced in the circuit, but the direction of current will be opposite to the direction in which the current was produced previously. That is, when closing the circuit, the direction is from this direction, but we will see when it is open. Now you can see the direction of current is opposite to the direction in which the current was produced previously. So you can see that at the make and break of the circuit, a EMF is produced in the secondary coil. Now, if I keep the circuit closed and if I move this coil closer to this, then again you can see a current will be produced. That is by the movement of this coil. That means there is a current already passing through this coil when the key is closed. Now, when a current carrying coil is there, you know, according to Oersted's experiment, there is a magnetic field surrounding this. When you are moving this coil with a completed circuit, moving towards another coil, which is simply connected to a galvanometer or a bulb, you can see that the bulb will be glowing, or the galvanometer will show a deflection as this coil is moved closer to this coil, which means that the magnetic field that is associated with this coil is coming in connection, or that is getting linked with the secondary coil, which is producing an EMF in the secondary coil. Now you can see there is a rheostat connected here. If you move the rheostat, you know the current in the second primary coil is changing. And if you just move the rheostat, again you can see there is a deflection, there is a current produced in the secondary coil. So here all these points are concluded. If you observe all the things that we have noted till now, you can see that the current starts flowing in the coil only when there is a change in the magnetic field associated with the coil. That is, in the first experiment, you have seen that magnet moving towards the coil. The magnetic field associated with the magnet is getting linked with the coil. There is a current produced. Now you can see when the magnet is remaining stationary in the coil, there is no current. That means there is no movement, means there is no change in magnetic field. Now when the magnet is moved out of the coil, again what happens? The magnetic field linked with the coil is changing. Or you can say the magnetic field associated with the coil is changing. Or you can say the flux, the magnetic field lines that are passing through the coil is changing, which we call as the flux, which we call as the flux linked with the coil. So, or you can see whenever there is a change in flux, a current is generated or an EMF is induced, and this EMF is called as the induced EMF, and the current so produced is called as induced current. So you can say the Faraday's laws were put forward based on his experiments and based on his observations. By taking all the conclusions together, he had forward his laws in the name Faraday's law. Move further towards Faraday's laws. The first law says that whenever there is a change in magnetic flux in a closed circuit, an EMF is induced in the circuit or produced in the circuit. When an EMF is produced, you know naturally there is a current produced in the circuit, and the current so produced is called as induced current. This is called as Faraday's first law. This is simply a qualitative law which says that whenever there is a change, an EMF is induced. So it doesn't mention anything about the quantity of the EMF. So it is called as a qualitative law. Whenever there is a change in magnetic flux, an EMF is induced in the circuit. Moving further towards the Faraday's second law. According to Faraday's second law, it states that the magnitude of the induced EMF produced in the circuit is directly proportional to the rate of change of magnetic flux linked with the circuit. The rate of change of magnetic flux. If we represent phi as the flux linked with the circuit, then rate of change of flux can be represented as d phi by dt. So you will write it as E is proportional to d phi by dt. EMF produced in the circuit is represented as E, and it is proportional to d phi by dt. Now, if you substitute the proportionality sign by equal to sign, we have to multiply this by a constant k. So you will get the expression E is equal to K into d phi by dt. Now substituting the values of E and d phi by dt, you find the value of K to be equal to 1. So substituting the value of K equal to 1, we get the final expression for Faraday's second law as E is equal to d phi by dt. And what is the unit in which E is measured? E is measured in the unit, all of you know, it is the EMF, and therefore it is measured in volt. And what is the unit of rate of change of flux? Flux is measured in the unit Weber and time is measured in seconds. So the unit of d phi by dt, you will get it as Weber per second. That is the statement of Faraday's second law. Now coming to the direction, you have already seen that in the previous experiments, demonstrations, when the magnet is moving towards the coil, what happens? You can see the direction, induced EMF's direction is always in such a way that it opposes the cause that is producing it. That is, when a magnet is moved towards the coil, that we will explain about this LENZ'S law in the coming slide. First, we will just say about the direction of the induced EMF. Applying it to Faraday's second law, we will get the equation as E is equal to minus of d phi by dt. This is applying, that is, you are used according to Lenz's law. It says that the EMF induced, that is E, is in such a way it opposes the change. What is the change? It is the flux change. The change in flux has to be opposed by EMF. So EMF and d phi by dt are opposite to each other. That is the direction of induced EMF in such a way that it opposes the change, that is d phi by dt will be opposed by the induced EMF. So you can write E is equal to minus of d phi by dt. Now if we consider a coil, there are n number of turns for the coil, and if we assume that phi is the flux associated with a single turn of the coil, then if there are n number of turns for the coil, then the flux associated with n number of turns of the coil will be equal to n into phi. So the EMF induced in the coil, which is having n number of turns, will be represented as E is equal to minus of n into d phi by dt. Now you know Lenz's law is also in accordance with the conservation of energy. We will see the next. Moved towards a coil, current is produced in the anti-clockwise sense. You mean to say when this north pole of the magnet is moving towards the coil, current is produced in the anti-clockwise sense. Means it will be acting like a north pole. See, if you are facing a coil carrying current, if the coil is carrying current in the anti-clockwise sense, it will be acting like a north pole. And if you stand on the other side of the coil, which will be where the current is moving in the clockwise direction, there that face of the coil will be acting like the south pole. See here, if you just view this again once again, you can see when the north pole is coming in, it is acting like a north pole. When it is moving out, the direction of current is changing and it is acting like the south pole. Means this coil, when this magnet is coming near the coil, what happens there? The magnetic lines of force coming towards the coil, and the coil doesn't want that change to take place. Means the coil, there is an EMF induced due to the flux linked with the coil. When magnet is moving towards the coil, the magnetic flux gets linked with the coil and the coil doesn't want this change to happen, or the EMF that is developed due to the movement of magnet towards the coil will oppose further movement of the magnet towards the coil. That means the coil, once the current starts moving, it is moving in such a way that it acts like a north pole. That means the EMF induced in the coil makes the coil like a north pole to oppose the movement of the magnet towards the coil. Or when the magnet is, we are moving the magnet away from the coil, means the coil, the magnetic lines of force linked with the coil is moving away from it. That again causes a current in the coil in the opposite direction, so that it wants to oppose the movement of the magnet, which is producing the induced EMF. So when the magnet starts moving in the opposite direction, means it doesn't want the magnet to move away, means the coil has to act like a south pole, then it will be keeping the magnet towards it. That is why the current is in the clockwise direction when the magnet is moving away from the coil, or it will be acting like the south pole, which is attracting the magnet towards it. So that is, you can see the Lenz's law gives the statement in such a way that the EMF that is induced in the coil is always opposes the change that is producing it. The change will be opposed by the induced EMF, or you can say the Lenz's law is in accordance with the conservation of energy. Or you can see when the magnet is moved towards the coil, if the coil is not opposing it, what happens there? Without any expenditure of energy, there will be further increase in the flux here, and as the magnet is coming in, and further movement, more and more current will be flowing through the circuit without any expenditure of energy, which is against the conservation of energy. Here the electrical energy is produced against the work done against the mechanical work done in order to move the magnet. That in that way the current is produced in the coil, which opposes it. And therefore you can say Lenz's law is in accordance with the conservation of energy. If the coil is not opposing it, which means that it is against the law of conservation of energy. So you can say Lenz's law along with Faraday's two laws. That is, there are three laws now: Faraday's first law, Faraday's second law, and Lenz's law. These three laws together is called as laws of electromagnetic induction. And the law of Faraday's first and second law is Faraday's laws, and Lenz's law, all three together is called as laws of electromagnetic induction. So this statements of these laws and the concept is clear, and therefore these are the main questions that is asked for the board's exam. Normally the statement of Faraday's laws, or it can be asked like what are the laws of electromagnetic induction. You just observe the Lenz's law in action. You just observe the next video, and you will get to know how Lenz's law is applied, and also the Faraday's law once again.
The equipment consists of a coil of copper wire. It has a ferromagnetic core extending out from the centre of the coil. The coil is connected via a switch to a 240 volt 50 Hz AC supply. There are several aluminium rings of different thicknesses. First, a simple demonstration of Faraday's law. A light bulb is wired in series with a second coil of wire. When the current is switched on, the bulb lights up. What's the explanation of this behaviour? We know that a coil carrying a current will give rise to a magnetic field. And Faraday's law says that where there's a changing magnetic flux passing through a conducting loop or circuit, an EMF will be induced. causing a current to flow. And so the bulb lights up. In this demonstration, it might not be immediately obvious that the magnetic flux is changing. But remember, our coil is connected to an AC supply, so the current flowing through it is varying sinusoidally with a frequency of 50 Hz. And so the magnetic field that it produces also varies sinusoidally at the same frequency. Now, for a more dramatic demonstration of Faraday's law and the effects of Lenz's law. When the current is switched on, a magnetic field is produced that induces a current to flow in the aluminium ring. Like all currents, this induced current will produce a magnetic field of its own. Now, Lenz's law states that the direction of any magnetic induction effect is such as to oppose the change producing it. So the direction of this induced magnetic field must be in opposition to that from the coil. The ring experiences a repulsive force and is launched into the air. We can easily show that the force launching the ring into the air comes from an induced current flowing in the aluminium ring. This time there is a gap in the ring. It isn't a complete circuit, and so no current flows. Now, what would you expect to happen if we repeat the experiment with the original ring, but this time we cool the ring first? You should recall that when we cool a conductor, its resistance decreases. This means that the induced current that flows in the ring is much larger, and so the repulsive force experienced by the ring is also much larger. We've seen what happens when a ring is placed right on top of the coil and the supply is then switched on. What if we start with the current already flowing and then place a ring over the ferromagnetic core? The principles at work are just the same. The current induced in the ring due to Faraday's law produces a magnetic field that is in opposition to the field from the coil. The difference is that in the previous demonstration, the ring starts very close to the coil, and so the repulsive force experienced by the ring when the current is switched on is very large enough to launch it into the air. In this case, the ring hovers at an equilibrium point where the downwards force due to its mass is balanced by the upwards electromagnetic force. So what if we replace the ring with a thicker one, with a greater mass? Despite being significantly heavier, the thicker ring seems to levitate at roughly the same height as the thinner ring. The reason is once again related to the resistance of the ring. The greater cross-sectional area of the thicker ring gives it a lower resistance, and so the current induced in this ring is bigger than the induced current in the thinner ring. So the increased weight is balanced by a larger electromagnetic force due to larger current. The explanation of the jumping and levitating rings presented here is useful as an illustration and reminder of Faraday's law and Lenz's law. It should also remind you of a couple of key facts about resistance and about magnetic fields due to current carrying coils. Actually, the explanation given here is somewhat simplified. If you're happy with the concepts explained here, you might want to think a bit more deeply about the following. Think carefully about the nature of the magnetic field produced by an alternating current.
Thank you so much. Drop your doubts in the comment section.